Welcome to our quantum deep dive. Today we're plunging into a concept that really flips our everyday understanding of information right on its head. It's called the No-Deleting Theorem. Imagine, if you will, a universe where data, information, it could never truly be erased.
Sounds like sci-fi, almost.
Right. But it's not. It's apparently a fundamental principle of quantum reality. So our mission today is to unpack this idea. Why is it that quantum information, unlike, the files you drag to the trash bin, just cannot vanish?
Yeah, where does it go? Or does it?
Exactly. And we're drawing our insights today from a really insightful essay by Yorgo Schneepat. So let's dive in. Okay, so to start us off, what is this no-deleting theorem at its core? Because honestly, for most of us, deleting information seems simple. Backspace, empty recycle bin, gone.
Right. Poof.
Yeah, poof. What makes quantum info so permanent?
Well, that's a fascinating bit, isn't it? The no-deleting theorem, it directly challenges that classical intuition we all have. Basically, it's a fundamental rule in quantum mechanics. It says you absolutely cannot completely delete any arbitrary unknown quantum information.
Okay, arbitrary unknown. What does that mean exactly?
It means if you have a quantum state like a qubit, but you don't know precisely what state it's in. In our normal world, shred a document, wipe a drive, overwrite data, it's gone, practically speaking.
Sure.
But in the quantum realm, with this unknown qubit, you just can't make it disappear into nothingness without leaving some kind of trace or messing with the rest of the system it's connected to.
So no clean getaway.
Exactly. There's no universal quantum eraser that just takes any unknown state and reliably turns it into a blank slate, like a zero, without affecting anything else. It's just not allowed by the physics.
That's already bending my brain a bit. So does this no-deleting thing have, a partner in crime or maybe an older sibling in the quantum world? How did scientists even land on this? It feels so anti-intuitive.
It absolutely does. And yes, it has a very famous sibling, the No-Cloning Theorem. You can't copy unknown quantum states either.
Right. I've heard of that one.
So this no-deleting theorem, it was formally proven quite a bit later, actually, in 2000 by Arun K, Pati and Samuel L. Braunstein.
2000, so much later than no cloning.
Yeah, almost 2 decades after no cloning, which was back in 82.
Wow.
And that gap, it kind of tells you something, doesn't it? It shows how subtle and, weird quantum information really is. It forces us to rethink these basic ideas about data. And if you zoom out a bit, you see it's part of this whole family of insights. You've got no cloning in 82, no deleting in 2000. Then there's even a no hiding theorem from 2007.
Hiding.
Yeah, basically says information can't just vanish into some hidden corner or get completely lost in the environment without a trace. All these, plus things like quantum entanglement, they all point towards this really strict conservation law for quantum information. It's not created, it's not destroyed, it just changes form or moves around.
Okay, so it's conserved, but why? Why does quantum information behave so differently? What are the quantum rules making deletion impossible?
It really boils down to a few core quantum principles that just don't match our everyday world. First up is superposition and quantum coherence.
Okay.
So unlike a normal computer bit, there's definitely a 0 or a 1.
Like a light switch, on or off.
Exactly. A qubit can be sort of both at the same time. It's in a superposition. Think of it like a coin spinning in the air, its heads and tails until it lands.
Got it.
This ability, this quantum fuzziness, we call it coherence. It's crucial for quantum computing, quantum cryptography, all that stuff. But it's also super fragile.
Fragile how?
Well, if this qubit in its delicate superposition state interacts with almost anything from the outside world, heat, vibration, even a stray light particle, it kind of collapses. It loses that bothness.
Decoherence.
That's the one. Decoherence. It's like the spinning coin suddenly landing before you were ready. And this leakage of information into the environment is a massive headache for building stable quantum computers. Then there's entanglement, Einstein's spooky action at a distance.
Right, the weird connection thing.
Yeah. 2 or more particles get linked in this deep way. Their fates are tied together no matter how far apart they are.
Like those synchronized coins you mentioned.
Exactly like that. If one lands heads, you instantly know the other, miles away, is tails. They share one description, one fate. And no deleting is key here too. Because information can't be deleted, it stays conserved even in these entangled systems. You can't just snip out information from one part without affecting the whole interconnected web. It adds to the security, you see.
Okay, so superposition, entanglement, what else?
The big one is quantum measurement itself. It's fundamentally different from classical measurement.
How so?
Classically, you look at something, you measure it, it stays the same. Check a thermometer, the temperature doesn't change because you looked. But in the quantum world, the very act of measuring, of looking at a particle in superposition, forces it to choose.
It collapses the superposition.
Precisely. The spinning coin has to land. It picks heads or tails. And here's a kicker. Once it collapses, you can't just rewind and put it back into that exact original fuzzy superposition. The measurement itself changes the reality irreversibly.
Irreversibly. Okay, that sounds important for deletion.
It's critical because classical deletion often involves irreversible steps, like overwriting. But if quantum measurement is irreversible and fundamental quantum evolution is actually reversible, well, you see the conflict.
That is a fascinating distinction. So boiling it down, what's the absolute core difference between the classical bits we use every day and this quantum information?
It's night and day, really. Collectible info. Discrete zeros and ones, on or off. You can copy it perfectly, delete it easily, send it wherever.
Standard stuff.
Quantum info. Based on qubits in superposition, that fuzzy both state. Can't be perfectly copied, that's no cloning. And crucially for us today, can't be perfectly deleted. That's no deleting. And like we just said, measuring it changes it fundamentally. That doesn't happen classically. Which brings us right back to unitarity. This is a central pillar of quantum mechanics.
Unitarity. That sounds mathematical.
It is, but the concept is key. It basically means that for a closed, isolated quantum system, its evolution over time is perfectly reversible. Like running a film forwards and backwards, no information is ever truly lost or gained within that closed system.
Okay, like a perfectly preserved recording.
Exactly. And this no-loss rule is precisely why you can't just delete quantum info the way you delete a file. Deleting a file is usually an irreversible process, right?
Yeah.
You overwrite it with zeros. You can't easily run that backward to get the original file printed.
Right, it's destructive.
But that kind of irreversible, destructive process isn't allowed by the fundamental rules, by unitarity, for a closed quantum system. So the no-deleting theorem follows directly from this. Complete deletion would have to be irreversible, and quantum mechanics says nope to that for isolated systems.
So this total reversibility, the unitarity, underpins both no-cloning and no-deleting. It sounds like they really are two sides of the same quantum coin.
They absolutely are. A dynamic duo, you could say, linked by the fundamental mathematics of quantum theory, linearity, and unitarity.
Linearity.
Yeah, basically meaning quantum operations scale nicely, which also prevents simple copying or deleting operations from working universally. So no cloning says you can't copy an unknown state. No deleting says you can't erase an unknown state. Together they tell us something profound. Quantum states aren't just things you can duplicate or eliminate whenever you want. They are preserved. They evolve. Information, in this quantum sense, persists.
That idea of persistence, it makes me think about energy. There's the Landauer principle, right? Saying deleting classical data costs energy. How does no deleting fit with that?
Good connection. Landauer's principle says deleting classical bits must dissipate a minimum amount of energy because you're reducing the number of possible states, increasing order locally, which means you have to increase entropy or disorder elsewhere, usually as heat.
So deleting costs energy.
For classical bits, yes. But the no-deleting theorem changes the game for quantum information. It says you can't delete it in that irreversible way in the first place. So the cost of deletion in the Landauer sense, well, it doesn't apply because the action itself is forbidden.
So no cost because no deletion.
Pretty much. Instead of being deleted, quantum information gets redistributed. Think of decoherence again. The information about the qubit state doesn't vanish, it leaks out and gets entangled with the environment.
Like that drop of ink spreading in water.
Exactly. The ink is still there, just spread incredibly thin, mixed with everything else. The total information in the combined system, qubit plus environment, is conserved. It relates to quantum entropy. The information is still accounted for, just rearranged and much harder to access. It's conservation again.
This is genuinely deep stuff.
Yeah.
Okay, let's pivot to the practical side. These are fundamental rules, but how do they actually impact things like, building quantum computers or sending secure messages? What does this mean for technology?
Oh, the consequences are huge.
Yeah.
Really shaping the whole field of quantum informatics. Let's start with security in quantum cryptography.
Okay.
Because of no deleting and no cloning, once quantum information is used, say, to share a secret key, an eavesdropper can't just copy it without disturbing it, no cloning. And they also can't somehow intercept and delete it cleanly without leaving a trace, no deleting.
So it makes eavesdropping detectable.
Exactly. In protocols like BB84 quantum key distribution, Any attempt to measure the quantum bits carrying the key inevitably disturbs them. The sender and receiver can detect this disturbance because the eavesdropper couldn't have perfectly copied or deleted the original state. It's built-in security, thanks to these fundamental rules.
That's clever. What about inside quantum computers themselves?
Well, that's where it gets challenging, too. Quantum computers are incredibly sensitive to noise, to decoherence, right? Information constantly tries to leak out or get corrupted.
A fragility problem.
Yes. And since you can't just delete the errors that creep in, you need a different strategy. This leads directly to quantum error correction.
Ah, fixing the errors instead of deleting them.
Precisely.
Yeah.
You can't erase the error, so you encode the fragile quantum information redundantly across many physical qubits. Think of it like making multiple quantum backups in a very clever, entangled way.
Using things like the short code or surface code.
Exactly those kinds of codes. They allow you to detect and correct errors by measuring parts of the system without destroying the core information you want to protect. It's all about preserving the information, because you can't just erase the mistakes.
So it forces a completely different approach to fault tolerance.
It really does. And it creates challenges for quantum computing design. Classical computers just overwrite memory constantly. Delete, reallocate. Easy.
Standard memory management.
Can't do that so easily with qubits. You need new ways to sort of reset or recycle qubits without true deletion. Maybe using reversible quantum gates, or exploring entirely different architectures like topological quantum computers, which have some built-in protection.
Right, finding workarounds for the no-delete rule.
And it pushes the development of new storage and transmission mechanisms. How do you store quantum states long-term? How do you send them over long distances without decoherence destroying them? This leads to research on quantum repeaters, better quantum memory.
It all ties back to the information being persistent but fragile.
Exactly.
Yeah.
And ultimately, for the future quantum internet, this theorem is foundational. It underpins the security and reliability needed for quantum communication, cloud quantum computing, distributed quantum tasks. Information persistence is key.
This really is mind-bending. If information is fundamentally indestructible at this level, what are the really big questions scientists are still wrestling with? Are there any loopholes or exceptions?
That's where it gets even more fascinating, pushing the boundaries. One key point is the theorem strictly applies to closed, unitary systems, perfectly isolated.
Which isn't realistic, right? Systems always interact.
Right. In open systems interacting with an environment, information appears to get lost due to decoherence. But as we said, it's more accurate to say it's redistributed, spread out, entangled with the environment. So is it truly gone? Or just incredibly hard to retrieve? Most physicists would say it's still there, just diluted.
So practically lost, but fundamentally conserved.
That's a good way to put it. The information's signature is imprinted on the environment.
Where else is this theorem really tested?
The ultimate test bed is probably quantum gravitation and black holes.
The information paradox.
Exactly. What happens to the information that falls into a black hole? If the black hole evaporates via Hawking radiation, does the information vanish forever? That would seem to violate quantum mechanics, including the implications of no-deleting.
So no-deleting suggests the information must get out somehow.
It strongly suggests it can't be truly destroyed. This lends support to ideas like the holographic principle. Maybe the information is encoded on the black hole's event horizon and gets released, scrambled, in the Hawking radiation. It's a major puzzle at the intersection of gravity and quantum theory.
Wow. So what's next for research on the theorem itself?
Well, definitely more experimental verification. Directly testing no-deleting is hard, but as quantum control gets better, we can design more precise experiments. Also, exploring generalizations, what happens with mixed states or states that aren't perfectly orthogonal. And of course, finding new applications in quantum algorithms, maybe new cryptographic protocols we haven't thought of yet.
So, wrapping this up, the core takeaway seems clear. The no-deleting theorem isn't just some obscure rule. It's telling us something profound about reality, that quantum information is fundamentally conserved, not destroyed.
Absolutely.
And that has these massive ripple effects, changing how we think about everything from computation to cosmology.
It really does. And maybe a final thought to leave you with. Consider what it means if information at this deepest quantum level is truly indestructible. It changes our whole conception of memory, of data, maybe even of existence. If information can't be truly erased, only transformed or redistributed, what does that imply? It suggests a universe where every interaction leaves a permanent, though perhaps scrambled record woven into the quantum fabric. Nothing is ever truly forgotten by the universe.
A truly mind-expanding thought indeed. Well, thank you for guiding us through that, and thank you all for joining our quantum deep dive today. Remember, this fascinating exploration was grounded in the insights found in an essay by Yurgo Schneppat.
Really interesting work.
Definitely. You can explore more at schneppat.de. That's schneppat.de. Until next time, goodbye.